And we have the session Fusion in Belgium. And that means that the various representatives from the national labs and from the universities with activities in fusion are going to give you a very quick overview of what their activities entail. So first up we have Dr. Maarten Vergote, and he's a researcher and also professor at the Laboratory for Plasma Physics at the Military Academy in Brussels.
Yeah. Yes, thank you for the nice introduction. So on behalf of Professor Van Schoor, our director, I'm presenting here the Laboratory for Plasma Physics of the Royal Military Academy. As maybe not too many people in the room know our institute, just a little word on this. We're located in Brussels, close to Schuman, the headquarters of Europe. And we produce officers, students, to serve afterwards in the army. They are produced with an academic degree, university level, masters of engineering, and so we have an academic department, but also research part or research group on fusion, of course. So we have had our talk about fusion from Jeff. I will not comment on this. You have heard all about it. We work on the heating, of course. In order to get fusion, you need to heat the ions. And here is a representation of what will be in the next future ITER. You have to heat ions in order to overcome the Coulomb repulsion, of course. There are several options. First, with this red arrow that you see over here, you could rely on simple ohmic heating, so drawing electric current through the plasma, which is a highly conductive medium. You can get some heating, but that won't bring you that far. It's simply not efficient enough. The better stuff is here on the right-hand side with neutral beam injectors. They launch in a more or less tangential direction neutrals into the plasma, and so they try to heat by friction the plasma there. And so last but not least, you can try to heat the particles themselves, be it electrons in ECRH, or electron cyclotron resonance heating, or ICRH, ion cyclotron resonance heating. So immediately heating the particles. In our case, we are focusing on ICRH, of course. Directly the ions. It's done when electromagnetic waves with the proper frequency, a frequency that matches exactly the cyclotron movement of the particles around the magnetic field lines. So we have chosen, more or less half a century ago, that line of direction, or that philosophy. We're, let's say, convinced that makes sense. In the end, you have to fuse the ions, of course, so let's heat the ions. Okay, but, so this one here. Next to ion cyclotron resonance heating, antenna realization, and the theory about it, around it, we have done a lot of other things. Well, most of these things on this short list of our track record of the lab have at least some link with the ICRH, but not all of them. Most of them have by now been closed, all these lines. Actually, the last two here on the, oops, I have to go back. Here on the bottom right-hand corner, 9 and 10, these lines we still investigate further. So actually in our team we have people working on theory, the last point here. So theory of wave propagation in the plasma and wave absorption by the plasma. And then on the other hand, we have a larger group of, let's say, people that do the hardware technology. And they produce then, well, actually, in terms of the whole lab, we go from the workshop to the client machine installation of our ICRH antennas. Examples here are mentioned on Wendelstein 7X, the last one, but other ones as well. So in order to give you an idea of what we have done, it's not exhaustive, nor the list, nor the description with some pictures that I go through quickly by now. Let's catch up a little bit the time that we are behind schedule. So for us, things more or less started with some dimensions with Dekeyser in the 80s, 90s, with several versions, several generations of antennas. Dekeyser was a medium-sized tokamak located just across the border in Germany, Jülich. But we scaled up the knowledge, we scaled up the dimensions of our antennas by moving to JET. JET is still today the largest tokamak in the world in operation. Okay, and so there as well, we have installed several generations of antennas. As you can see on this picture here in the central position, you see the first antennas that were firstly installed already late in the 80s, the A1, A2 antennas. And then later on came the ether-like or the enhanced performance, the JET EP antennas, as you can see here on the right-hand side, with, of course, higher power radiated and power density, of course, radiated towards the plasma. So these antennas were in these world record shots that Jeff mentioned in his talk now last year, and then also before that in the 90s there. Okay, so with all, well, let's go back maybe 1 second. With all that knowledge of installing several versions of antennas, we, let's say, acquired quite some expertise in the field, and so, well, Jeff already mentioned that as well. So, in terms of heating of ions, you name an ion and we heat it in some sense. There is some knowledge that how to combine things. Here on the technological realizations, we have acquired quite some knowledge about things, how to do things in the future, also how not to do things in the future, or how to do things better in the future. And at some point, in such a way that in the beginning of this century, we were invited and we were actually taking, in some sense, the lead of the design of the ether antenna or ether ICRH launcher that is going to be built. Let's hope so. So as you can see here with these numbers here mentioned here, the power density further increases. The dimensions, of course, again, more or less doubles. You see the person compared to the person in Dekeyser or in JET, doubling with respect to JET, of course. So let's hope that this becomes reality in the upcoming decade. Now I don't have to tell you that, okay, these kind of installations, this is not sold and installed at the client machine as such. There comes always, quote unquote, some after-sales service. So in our lab we have people working dedicated to and working only to operate these antennas in situ in the client machine where they are installed actually. And so in this case, for instance, it was very, very much probable that young or less young scientists will move to ether. This is Cadarache in the upcoming decades to do experiments once the antenna is installed over there. Sorry. Okay. So that's not the end of the story. Up to now we have talked about installations in tokamaks, but since last year we also have an LPP ICRH launcher into a stellarator environment. And so Jeff mentioned that as well with even nicer pictures, but this gives you a little, let's say, simplification of the situation, simplification as much as possible, because it's a little bit much more, much more, I have to say. Complicated in terms of plasma structure. You see the arrow, the orange colored plasma column. And so this antenna, as you can, sorry, I have to move back. I have to push this button. Antenna antenna picture that you see on the left-hand side. It's not so very visible, but actually it's a completely 3D structure. So in terms of the two angles, there is curvature independent in the two angles with the antenna that can move. And so here as well, this antenna has been integrated, and from next year on, we get some experiments, and so there will be people working in Greifswald as well, and probably, very likely, we will see there new things, new physics that will show up, albeit only by the much more complicated structure of the absorbing plasma. So there are also a lot of new scientific work on our dish to do in the upcoming years. I would say it will be into the direction of the northern of Germany, W7X. By the way, I have to mention that probably, well, not probably, that in this context there will be one position actually opened in the next future in our laboratory in this scientific work on this W7X project an ICRH antenna that is positioned over there. Okay, so. We are always looking for new people, new, young, talented collaborators that could join and strengthen our team. In much of the cases, these are PhD candidates or young starting PhD candidates. And of course, it is impossible, completely nonsense to think that such starting PhD students could claim shot time in these huge international facilities like JET or W7X or in the future maybe ITER. No question about it. This is impossible. So for that reason, we have now since some years an agreement with the Germans to be able to operate a small machine just across the border where actually Textor was placed in the past. So it's the Thomas device. Daniel talked about that and works on that as well. And so actually that gives you a good view on how a starting PhD student could start off with his research. New ideas can be tested there very, let's say, fluently and very independently. We can manage our time there, let's say, by ourselves, and we don't have to let's say, take into account other schedules. So that's more or less it. Thanks a lot for the opportunity for presenting our lab.
Thank you very much, Dr. Vergote, for the very nice overview. Any questions?
I just have a small question, like what's the average, let's say, lifespan or time that it takes for master or PhD in this case to start working on JET or ITER project?
After reaching or having obtained the PhD, you mean, or?
Yes, or during the PhD, since you mentioned here that PhDs starting don't work on the ITER project, which is of course logical. I was just wondering how long it takes for somebody to start working on these projects.
Well, it depends on the subject that is in the discussion, of course. So you cannot, let's say, fix a time gap on this evolution. No, this is impossible. It takes time. Of course, if you have a nice topic during, you have done research onto a nice topic during your PhD, and that appears to give very nice results that can be, that should be tested in a bigger environment that could be picked up by people from ITER. Why not? Or this is hypothetical, but it must be really a brilliant idea and with nice results on the smaller machines in order to, because these structures ITER, for sure, these are so complicated and so packed up with already so much diagnostics that it's really complicated to get in something new. Yeah. And it's not constructed yet.
If I may also comment, I think what Mr. Van Spouwen also meant is that it's not only about testing something new in ITER. Of course, PhD students definitely work in a team, of course, on data or on experiments that are being applied within the scope of their PhDs at present-day machines. So they can, of course, can be involved in that. Yeah.
Right.
All right. I'm afraid we'll have to move to the next talk. So let's thank Dr. Vergote again. Next is Dr. Dmitry Terentyev from the other national laboratory, so the Belgian Nuclear Science Center in Mol, and I'm happy to give you the word.
Am I on there? Okay, thank you, Mirel. Perfect, and thank you, Geert. It's a fusion research and development and also science center, as you see. The objective of the presentation is to tell you, first of all, why we do fusion, explain to you how, and what is expecting us in the future here within next 10 to 15 years. I'm not sure which of you is aware where we are. That's what you can see on the Google Maps. We have 3 nuclear reactors on site. Therefore, we decided to stay close to the Dutch border. And if you take a look at the picture taking what you call helicopter view, which was a real helicopter back then, in 2005, that's what you could see. This is by the, I can't really use the laser pointer, that's a pity. The smoke you see is coming from a coal plant, and of course nuclear reactors don't smoke, that's clear. There has been fantastic presentation by Jeff. I think ERM KMS has given enormous contribution to how to burn plasma, how to control plasma, how to install that devices, and they are for sure best travelers. You've seen a lot of outsource of science. I'll tell you what you can do in Belgium for fusion here, today, in Belgium, using Belgian facilities, working with Belgian technicians, and in the future, how we all together can move. Let's start with the jet. And I promise you it's the last time I show the jet, only once. Why I show it is to explain what about materials. Clearly you can see discharge. It's a very well-known movie. Everyone can get it on YouTube. What you have to learn from this movie is plasma burns the wall, the vessel, non-uniformly. You see the cooling piece, that's called diverter. And as you have a plasma discharge, the plasma is unstable. So what is our then problem? Our problem is how to put a sun in the box that you can see there on the left-hand side, such that the sun will give you a stable heat. Because anything that is unstable causes fatigue. And fatigue means limited lifetime. And limited lifetime means danger of your investment. At the end of the day, you have to think about the money that the investor will bring in order to build a power plant. No money, no fusion. And that means that we need to, on one side, know how to burn the plasma correctly, and on the other side, we have to make that box. And we are working on that box. That's our function. What's the problem there? The problem is that when you have a fusion reaction, the energy, the electricity you're going to get from the neutron, 14 MeV neutron. It's not a helium, it's not a hydrogen. That is just to keep plasma burning. But it's a neutron that's getting slowed down in the walls, give the heat to the walls, and then you extract away this heat. This is what gives you electricity. And the problem is that the more you use those neutrons to heat the material, the more lattice damage you're going to create. It's just a displacement of the atoms. It's the holes and interstitials. But as a result of those displacements, if you take initially good material, what means good? It means safe. It's like when you drive on a bicycle, you don't want your bicycle to be crashed where you drive over the hump. Exactly the same way, when you take a material and you pull it, you can measure the strength and you see how controllable it is bending or pulling. But as you irradiate it, in fact, this control is getting lost. And our function is to investigate how those processes are taking place in those materials and to bring it to the design code so that you can tell to engineers, please use that material in this, and that conditions, such that he can calculate and come to the investor. And the investor can decide, should he pay for fusion or should he not? And that's our role. In practice, speaking of the real components, we are concerned with the two. One is the tritium breeding blanket, which is the device that on one hand extracts the heat, but on the other hand also produces tritium. It's nothing but a pipe. It's a pipe where you have lead lithium flowing, and lead lithium can give you, let's say, a dual function. It can take away the heat as well as it can generate tritium, thanks to lithium. The other is diverter. Diverter is just to plate the tiles of tungsten, and then there is the water flowing underneath. And the function of the diverter is to evacuate the heat. But as I told you, and as I've shown to you on that movie, because of the fatigue, because of the instabilities in the plasma, you have to make sure that those components will be durable. And the way to make sure that those components will be durable is to diagnose the plasma and possibly control it, so that when it comes out of the control or comes out of the parameters that we don't want, we can return it back and keep operation. Then, what do we do? How do we investigate materials? As I said, the energy will be produced by the neutrons. Therefore, you must have test capabilities where you have field of neutrons. For that, we have BR2, Belgium reactor number 2. That's now operating for nearly about 60 years. And there, in that reactor, we use a conventional fission reaction, just a uranium fission. But thanks to that, there are neutrons that are flowing, and we can take use of those neutrons to expose the samples. And just to give you to give you an understanding of the scale, that's the reactor building, so it's about 7-floor building. That's the reactor pool. It's a 6-meter tall pool, and it's about 3 meters in diameter. That would be the device which you will put in one of the channels, so all those multiple things you see are the channels, and you would put it inside so that you can mimic the ether relevant conditions. Then you would take the sample out, and that would be the dimension of the sample. Why it's so small? Because it's quite active. So neutrons give some residual activity, and the smaller the sample, the better for you to work with it. And if you want to look at the microstructure, at what happened, this lattice damage, what I told you, we have to go to a scale of about 20 micrometer, often even lower. So this gives you the idea of how we go from a 7-meter tall building to 20 micrometer high sample. Then, as we need to test the samples, please don't touch them by the hands. So everything, all complicated and, let's say, fancy devices that you can see now that people are selling, you have to think and design how you bring it to the hot cells that will protect the researcher. For instance, this gentleman standing behind the window. By the way, this window is 1 meter thick. It's a LED window, 1 meter thick. And he's doing everything, completely everything with the manipulators. It's let's say this is a research in itself, but fusion absolutely needs the fruits of that research. Then, in principle, the characterization of the damage goes in 2 directions. One is the mechanical characterization, where we get the modification of the properties. For instance, here I show you the curve of the absorbed energy. This is the most conventional, the baseline curves. Thanks to that, we can continue, we can, let's say, make an extension of the nuclear power plants in Belgium beyond 2025. You have to demonstrate that with the dose accumulated, with the resource that we still have in the reactor, we can make a safe operation, so the absorbed energy, given that the lowest temperature of the operation of the reactor will not go below 0 degrees, will be satisfied. And we are using absolutely the same philosophy and also regulations in order to qualify fusion materials. And then we also look at the microstructural characteristics, where we use microscopes. Should they be electron, ion? Should we use a dedicated means in order to prepare the samples? There is a poster about it, and I welcome you to attend, just to tell you that, let's say, the objective of the microstructural characterization is to confirm the mechanical properties. So, as such, microstructural characterization does not come into the safety regulations. Then, there are 4 posters that we have today, and I'll just briefly explain to you what are the R&D directions that those posters reflect. First of all, it's about diagnostics. And at SEKCEN, Belgium Nuclear Research Center, we have developed a dedicated diagnostics for the plasma that can actually diagnose a plasma without time integration. So you really get, let's say, in situ or on-time signal. And it is achieved thanks to the, let's say, a development where we know how to generate the light source, then we put it through the magnetic field, it changes its special characteristics that we can read at the end of the fiber and understand what was the field. And the fiber, in fact, is not larger than the hair, and there will be a stand, so I welcome everyone to attend and see how it works. Second direction is the materials and mechanics. As I said, we need durable materials, not because we are crazy about good materials, because we need to financially justify, we need to be able to sell this reactor at the end of the day. And for that, we start with unknown materials, and we have some hypotheses of what we chemically would like to change in it. For instance, alter precipitation. Then we do, let's say, a study also involving some artificial intelligence sometimes, so that we could get the first guess, and then we can go to the company that's called OCAS, that's actually across the channel. It will take you only 20 minutes to reach that place. And we cost there the materials, we do thermomechanical treatment, and then we come to the chemistry and check whether or not we have achieved what we wanted to achieve. Then for the microstructure, we are using the tools that allow us to use atoms. I mean, no wonder these days many people can see atoms. And here I just would like to give you an examples of what it means to study microstructure. Here is the response, the microstructural response of the material that is in non-irradiated state, in reference state, and you see dislocations. These are 1/2, 1/1 dislocations. It's a BCC iron. But if you irradiate it, for instance, with neutrons, you will have a damage pattern. These are the bubbles. And then dislocations are bending around those bubbles. And that explains why your material becomes brittle, when it's no longer ductile as before. Very important thing I also wanted to say that we have an organization, internal organization that's called SEKCEN Academy, where every year we have a call for approximately 30 to 50 PhD positions. And in fusion, we are running about 7 to 8 PhD positions every year. And here I just list the contributions from the contribution that expertise is arranged with different universities. And also I mentioned the University of Ghent, which plays an extremely important role. And thanks to Ghent, we can also get an access to the OCAS, which is metallurgical company, a really unique opportunity for us. And then the last set of slides, the one that I promised you in the beginning. Let's talk a little bit about future, what we can deliver. On our side, we are constructing the mirror reactor. This has been already noticed by Jeff. And what means mirror reactor? Mirror reactor consists of accelerator and reactor as such. Accelerator gives us the protons, what is shown schematically on the picture. Those protons hit the target atoms, and that induces basically a spallation reaction, a fission reaction. And there, in that reactor, we will be able to achieve a specific condition that will represent fusion. I will come to explain to you what means specific condition, but before that, just let me give you an idea about the timeline implementation. Our currently operating test facilities will run till about 2035, so we are still having some, let's say, horizon to do the research with neutrons we have today. Then we will have an accelerator between 26 and 36, which will also enable us some extra capabilities. And from about 36 on, we will start commissioning of the reactor. And here I use this picture in order to give you an idea about the scale of the facilities. This is the 6-7 meter, not meter, but floor building, and that is over there on the upper left corner. And this is what will be constructed. So it's pretty impressive, in fact. What will it give to fusion? In fact, everything comes to the neutron spectrum, because you know the difference between fission and fusion is that in fusion you have 14 MeV neutrons, and this is the red peak that you can see here. So for instance, red curve describes the expected spectrum in DEMO. And with the currently operating reactor, like BR2 for instance, the problem is you don't have those high energy neutrons on one hand. That's problem number one. And problem number two is there are too many thermal neutrons with low energy. And because of that, conditions are not fully equivalent. We can go into details if necessary. I'm available during the reception with my great pleasure. But thanks to Mira, we can actually fix this problem. And that's our intention. And that's why we are pushing that the Mira is the future way how to make qualification of materials. Qualification means we give a driver's license to material to be used in future reactors. And this is my pre-last slide to explain to you how SCKCN moves and how development of ITER and demo moves on the same timeline. We are in 2022 now, and now we are in the phase of construction and licensing. And by 26, when the first political plasma will be issued on ITER, we will also make the first probably political beam on our accelerator. After that, ITER will move to the high power operation in about 2034, and this is when we also expect to commission our beam that's needed to burn the reactor. And in 35, 38, in fact, ITER is expected to go to Q10, so this famous, let's say, demonstration of the nuclear energy. And then we will be, shortly after that, we will be ready, in fact, to start qualification of demo material on our future facilities. And here is my last slide. I think I will save time. I will not read it for you. Please come to our posters. We are all available, and we'll be happy to see you also with the demonstration on Fox. And there are 3 lines for you to read while I will be taking the question. What is our strategy to work for fusion in Belgium? Thank you very much for your attention.
Thank you very much, Dr. Terentyev. Very interesting talk. Any questions?
Thank you, Dmitry, for the very interesting talk. Can you expand in a few words about the complementarity between IFMIF DONES and Mira for future testing?
IFMIF, DONES, and Mira. We should go in the reverse order. Mira will be constructed first, then DONES, then IFMIF. This is the complementarity number 1. There is a time complementarity. Complementarity number 2 is that it looks like the agenda of Europe is more agile as compared to Japan. And we cannot afford to wait for IFMIF to get lessons from it. That's why DONES is thrown in Europe. But we cannot even wait for DONES in order to make the decision for the primary heat transfer system in demo. Because we have to take this decision by 2035. And there, Mira is not yet operational. However, by combining the accelerators and fusion reactors, we can at least address helium effects thanks to accelerator. And we can use, let's say, large volume of radiation that will be accepted by safety authority, at least in France. We know that for sure. That's the complementarity. So time-wise, and I would say license-wise.
All right, thank you. Any other questions? Then we thank Dmitry again. Research. So our research unit is called Infusion, for inference, information. Indeed, because that is what we do. We develop data science methods, also developing new methods, not only using them and applying them in fusion. Started about 15 years ago. I mentioned that because this is a relatively young activity in fusion. It's a bit different from astronomy or particle physics. In fusion, this type of more advanced statistical methods, or even sometimes simple statistical methods, are just starting to be introduced. And, but it's going quick, so it's really a growing field. We pride ourselves on solid mathematical foundations. We think that foundations are important to be able to analyze how our methods work. and yeah, a broad range of applications. Yeah, what is data science? Perhaps I don't need to explain, but you hear various terms. Sometimes you might ask, what is the difference? Well, I also sometimes wonder. Statistics, pattern recognition, machine learning. Sometimes machine learning is a bit of a fancy name for statistics, but there are also additional methods in that field that are proper to that field. Artificial intelligence is also linked. So, broadly speaking, what does this entail? On the one hand, we do uncertainty quantification. The pointer does not seem to work anymore. Uncertainty quantification, quantify in an experiment, well, what actually every scientist does, but we use somewhat more advanced methods to quantify what is the uncertainty on a measurement. How does it propagate through measurement devices, through calculations? Time series analysis, obviously we have a lot of time series in Fusion. We also have multidimensional data. Here it's two-dimensional. In general it will be in higher dimensional spaces where you want to find structure, patterns, clusters, more continuous patterns, and also you want to model these patterns, and hence you want to estimate parameters of models, parameter estimation with uncertainty. So these are some of our applications. The one we started with already 15 years ago is integrated data analysis. This is also known as data fusion. So also fusion, but for data this time. We apply this to West, and also we are involved in studies for applying this to demo. Basically, this figure on the left illustrates that. You have a physical quantity that you want to measure, let's call it Q. It's inside the plasma, like it would be the density or the temperature or the magnetic field at a certain position inside the plasma at a certain time. Often there are multiple possible ways to measure that quantity. And we call these measurement apparatus, we call that diagnostics. So you have multiple possible diagnostics to give you information about some plasma quantities. So there is a certain redundancy in that, and that redundancy you can exploit in order to estimate in a probabilistic way the best possible value of the quantity in the plasma that is compatible with both or even multiple sources of data, so data fusion. For this we use Bayesian inference, and we come then to that joint probability distribution. So the added value is also that you get immediately the uncertainty. You do, in a structured way, uncertainty propagation. We apply this, for instance, for tomography, because tomography is also nothing but, well, there is a diagnostic and that measures, that looks inside the plasma along different lines of sight. The aim is to reconstruct what is in the two-dimensional cross-section, or even in 3 dimensions. How does the plasma, for instance, the density look like? These are synthetic data of emissivity from impurities, and you see it's quite challenging to reconstruct that and also get an error map. As I said, it always comes with error bars, so we have these error maps. This is one of the posters that we have here today, one of our PhD students, Hao Wu, so please feel free to visit him. I said parameter estimation, pattern recognition. One of the ways to do that is to estimate continuous patterns is regression analysis. And you might say regression sounds like some boring first-year statistics course. Yeah, it might, but there are also more advanced methods, Bayesian methods, even those grounded in geometrical techniques, differential geometry. So quite complicated techniques that we bring to bear to estimate in the best possible way trends in very complicated multidimensional data sets. We even developed our own regression technique, geodesic least squares regression, that has the advantage that it is both simple and robust. And simple is important because you want people who are not experts to adopt those methods. So as Jeff indeed already mentioned, we apply that to scaling laws, which are very simple models, like the one you see there at the bottom, power law models, we call that, and you want to estimate the parameters. But the data are very complicated and very unstructured, and still you want to find some structure in that. So people, that is also a bit the danger, apply statistics for that and find parameter estimates without much trouble. And maybe before I go to the next slide, I should mention this is also the topic of a poster of Joseph Hall here at the meeting. So we use these methods to do a revision of the well-known energy confinement scaling that was estimated 20 years, more than 20 years ago. And we found quite a few differences, and that's what I wanted to come to. You might say, for instance, what you see there on top is the confinement time measured in the plasma and predicted by the scaling law. And they should be equal, of course, ideally. So indeed, it lies quite well on that diagonal line. So you would say that seems not like a bad fit. And indeed, if you look at the estimates and the error bars you get from any statistical package that does regression analysis, error bars seem fine too. So you conclude that the dependencies of the confinement on these various plasma quantities is very well known, and you're starting to take decisions or design decisions on the basis of that, and people do that. That's where then the more advanced techniques come in, because if you do the analysis in a somewhat more advanced way, you will see that these true error bars are actually much larger, because these error bars assume that your model is correct, whereas you also have model uncertainty. And then you see these various dependencies with these extremely large error bars, and you see that actually only a few of them are quite well known, and some others, there hardly seems to be any dependence. And so this kind of analysis, you have to use the right methods to do that. So that's the message. People sometimes ask, what can statistics and machine learning do for a field like fusion? Well, a lot of things, but you need also the people to do it. And we see every day that a proper analysis can really make a big, big, big difference. So let me then quickly go over some other topics that we also treat. Modeling of stochastic events. Of course, you have a lot of stochasticity in fusion, plasma fluctuation, randomness, instabilities like these ELMs that were already mentioned, that can be compared a bit to a down-to-earth example of a pot of water you put on the stove, and the lid starts oscillating because the pressure builds up, pressure release, pressure builds up. That's, in a sense, completely different mechanism, physical mechanism, but also what happens in a fusion plasma, described in a poster by Jérôme Alhage. And what we do is we want to quantify the uncertainty. In this case, it's not really uncertainty, it's fluctuation. There is information in the fluctuations. We have statistical analysis of turbulence. Well, we do statistical analysis of these instabilities. And we see that you can recognize different regimes of ELMs, these edge-localized modes, by looking at probability distributions of their properties and then seeing how different they are. Then a more engineering-related topic, one could say, although you could also apply it to the plasma, is predictive maintenance. Well, this graph we always bring up because it sort of illustrates what you have on the left-hand side is what is called, with an expensive word, reactive maintenance. That means that you just, in a plant or in a production line or in a fusion power plant or a pump or a switch or whatever, you wait until something breaks. And then you repair it. Costs, delays. Slightly better is to do preventive maintenance. We're going to try to prevent that and do scheduled maintenance. Of course, then you don't know whether you're doing it at the right moment. Maybe it's far too early. It's not necessary. You're doing, again, overcosts and delays. So that's why in Industry 4.0, people more and more think about predictive maintenance by continuously with various sensors, measuring the condition of various components, various installations, and then with machine learning, looking at signals, time series, and trying to predict when an anomaly will produce. And we do that, as I said, we already did that in a few master projects on the turbopumps at Jet, big switches for the colloidal field at Jet, and now moving on to material components by looking at IR camera data. This is a poster by Leonardo Caputo, who has recently started working on that topic. And then finally, we have, again, a bit more in the relation to the plasma, real-time prediction and detection. Many of the techniques that we are now using, eventually, if you want to do that for demo, it will have to be done in real time, because you need to steer the plasma in real time. And for that, by the way, we will soon open a postdoc position to work on these real-time integrated data analysis for demo. So here is an application where we use a special type of neural network, explained in the poster by Azarak Jalalvand, postdoc collaborating with us. And so this type of neural network can very quickly be trained and adapted to new conditions. And that's what you sort of see there at the top. You see the density of the plasma at a certain position. And you see the line, the green and the blue line that track 500 milliseconds in advance what's going to happen in the future with the density in the plasma. Certain point, something happens, some anomaly, and you see that the neural network, the blue one that has been trained in advance, it doesn't adapt. The one that is able to adapt is also misguided for a short period, the green one, and then picks up again. Similar methods are also applied to detection in real time of instabilities, eventually also disruptions. Here is applied to detection and identification of alpha and eigenmodes. Close collaborations I also wanted to mention, of course, with the Laboratory for Plasma Physics. We have Professor Christel Crombé working on wall conditioning studies at Thomas. And then we are also involved in collaboration about material studies that were also already mentioned in collaboration with the Sustainable Materials Science Group of Professor Kim Verbeken at Ghent, who is the main principal investigator of Ghent in collaboration with SCK. And then very briefly, education. Well, you already heard a few alumni from our Fusion EP International Master. European Master of Science in Nuclear Fusion and Engineering Physics, 8 EU full partners where students go during each of their master year to study at a different university and also do their master thesis at real fusion institutes with which we have an association. Coordinated by Aix-Marseille Université, and very nice, a very strong alumni organization. And they give regular talks, so you can find it on YouTube or Facebook, and if you type in Fusion EP talks, you will probably find it. And alumni and also researchers give talks to alumni. Well, if you want to know more about that, we have the link to the website on top there. Fusion education means also PhDs. We also have joint PhDs with Padua University and Czech Technical University. There is the Mira Minerva, so linked to Mira, that was already mentioned, Fusion user community that maintains the interaction with the various universities. And this is coordinated by Professor Guido van Oost from our lab. Then we teach a number of courses, of course, also at local students, but also international students. There is this recent textbook about fundamentals of magnetic fusion technology, also co-edited by Professor van Oost. It's not quite yet in print, but you can already download a preliminary version. Voilà, and these are the details of, and also the website in case you're interested in, for instance, master thesis or PhD topics, then you're very welcome to contact us. Thank you very much.
Thank you very much for that very concise presentation, Professor Verdoolaege. Can we take any questions? Does anyone have any questions for any of the topics that was brought up then? Fantastic, lots of hands.
Hi Geert, very nice talk. I had a question a few years ago. You were mentioning the scaling laws, and you mentioned yourselves that they are dramatically simple for something as complex as a plasma. Now, a number of years ago, there were beginning efforts on trying with the kind of statistical techniques to try not only to do glorified curve fitting, if you like, but actually to find the kind of differential equations or whatever that are guiding the things that from our basic theory we haven't grasped yet or whatever, where then this type of statistical analysis could help point to some of these things. What is the status of that?
Yeah, so I think you're referring to the topic of, broadly speaking, system identification, but then applied to fusion plasmas, where indeed you try to learn from the data the governing underlying differential equations. We're not working on that at this moment. It's definitely an interesting research topic that we might explore in the future. I think we need both. So both the scaling laws, if you want to, I mean, more methods to compare what the plasma is actually doing and to predict, the better. There is a certain advantage in scaling laws that indeed is both an advantage and a disadvantage that they are very simple. That means that you also very quickly get a yardstick of how the plasma is performing and how it will be extrapolating. What we're also working on, and which you could also call a data-driven point of view, like the system identification, is to do model comparison, and that is going to be the next step to find better models from the data that, going step by step, that are a better fit over multiple regimes, both baseline and hybrid plasmas, better fit to the whole data set, because we know by now that the power laws they're not flexible enough, they can't capture that.
We do have one more question, perhaps we've got time for it.
Well, one more then.
Thank you, Professor Verdoolaege. May you go to the page 7, if that's technically possible? Maybe Mirel, Xavier. Yeah. I guess this question goes deep to your expertise. Yeah, page 7, yeah. So I did not understand. Did you manage to make fit better? And if you did, can you show us the result?
Yeah, so the result is on the previous page. This is what we derived. You will see that the error bars are roughly 10 times larger. And so this we obtained by taking into account additional model uncertainty. So put simply, what you do, you fit like a hypersurface of our hyperplane, you wiggle it. It's a very simple method to take into account the model uncertainty. You wiggle it until you obtain, you try to characterize when you will obtain a bad fit. And then you know something about the model uncertainty. And this eventually led to, indeed, increasing the error bars by a factor of 10. And then what I show then in this page, these error bars are the ones that we obtain, and that tell you that what is the dependence of the confinement on these global plasma parameters? Well, it's basically the current. It's probably not the density. It's the power that passes through the separator, the heating power, if you will. It's, of course, also the major radius. But out of these variables, it's not much more than that. Whereas before, a lot of conclusions were drawn from minute differences between parameters, because the error bars tell you that it is significant, whereas it is not. Okay?
Well,
all right.
Thank you very much again, Professor Verdoolaege.
Thank you. All right, thank you. And next we have And then, I need my notes. Of course, we have Dr. Wouter Dekeyser from Leuven University, and he's going to tell us what you're doing in research for fusion plasmas.
I hope you can hear me clearly like this. So indeed, I will present a bit an overview of the research we do at the KU Leuven with respect to nuclear fusion. And so this is research performed by 3 research groups, so collaboration between 3 groups mentioned here on the slide. 2 of them are at the Department of Mechanical Engineering, so the TFE and IDEAL groups, which specialize in thermal and fluid simulations and optimal design methods for a range of energy applications, including fusion. And then we have also a tight collaboration with the computer science department, specifically the scientific computation group, which focuses on specialized and efficient methods in scientific computing. So that has been a very fruitful and successful collaboration for several years. Let's see, okay. So what is our research about? So at Leuven we focus on what is called the diverter power exhaust problem, if you want. So we've already seen in fusion we try to generate a lot of power in the core of the plasma. A lot of that power, something like 80%, is taken out by the neutrons and goes directly out to the wall, but still some 20% of that power stays in the plasma and has to somehow safely be evacuated from the machine. And also the fusion products, so the reactants of the fusion reaction, have to be taken out, pumped away from the plasma. And so a large fraction of that power that is dumped in the plasma actually is then guided by the magnetic field towards the bottom of the machine to a specifically designed component, which is the diverter. And if you look at the power fluxes that you get there for future reactors, they tend to be of the order of 10 megawatts per square meter, which are enormous power loads. So to put that into perspective, these are often an order of magnitude higher than the typical power loads you get with spacecraft during re-entry in the atmosphere. And then the tricky bit is also that we have to sustain these power fluxes during steady state operations, so not just for a few seconds. Okay, so that's a really challenging problem. Of course, we want this hot plasma and we have to keep it away from the walls, and then we have to safely get the power out. That means that we need to devise somehow efficient operating scenarios where we can actually combine those 2 conditions between performing core plasma and a cold diverter with safe power exhaust. And we also have to look at how our power interacts with the vessel, because that also will have a feedback on how the power is extracted. Now there's one additional complication, and that is that all current machines are basically much smaller than future reactors will be. So we don't have experimental data that directly applies to the scale where we want to go. So that means that we heavily rely on so-called plasma edge models to predict how the power will exit the machine. And then we will use optimal design strategies to design those diverters. Okay, and so this is where the expertise of the groups come in. So in fact, we have been working on these optimal design strategies for various applications, not only fusion. So you see a few examples on the slide here. So on the top right, you see that you can have design problems where you want to optimally distribute cooling channels for microelectronics cooling, so really completely the opposite scale compared to fusion machines. You have there in the middle optimal design for thermal networks, where you also want to decide where to put pipings through streets to optimally distribute heat between producers and housings. And then you also see a few fusion applications like design of the monoblocks or design of the magnetic field. So what do all these applications have in common? Well, first of all, they all have aspects of very complicated modeling problems. They're multi-scale, they're multi-physics. That means they're very difficult to simulate, so you need efficient numerical methods to actually build your models and solve them reliably and in an efficient way, so that you don't spend ages waiting for the results. Then for all these problems, at some point you want to design a system, so you want to control some aspect of the system, which can be the shape, the topology. It can be certain parameters in your system that you have to optimize, so you need efficient methods to do that. And eventually, you want to, all these models will have some parameters that will be subject to uncertainty, and so you need to characterize what is that uncertainty on the parameters and then propagate that through the model so that you can do robust design that works not only in your intended operational point, but also in off-design conditions, for example. Okay, so when we apply that to the fusion application, the first thing that we focus our research on is on actually modeling the plasma boundary. So what is going on in this plasma boundary? Well, here you see a bit of a schematic overview of a tokamak plasma, and you see the reddish, brownish area in the middle. This is the core plasma, the hot piece where the fusion is going on. And then what we're interested in is the orange piece that surrounds this, which is the plasma boundary, which is in contact with the vessel and where the power has to be extracted. Now, one of the research domains that we work on there is on how to include the effects of turbulence in the models. Now, on the one hand, we want a model that's sufficiently reliable to predict how the power is coming out. At the same time, we don't want to be resolving all the fine length and time scales of the turbulence because it's simply not feasible at the scale of a reactor. So what do? We try to devise models based on so-called Reynolds average Navier-Stokes approach that you may know from hydrodynamic turbulence, where you effectively try to capture the average effect of the turbulent transport on the mean behavior of your plasma transport so that you can predict how it exits from the core and is transported toward the bottom of the machine, which is then the diverter. Then the next step of the modeling that we focus on is what actually happens there in the diverter. So at some point you have your plasma coming down from the core towards the diverter. And so your plasma, these are charged particles, ions and electrons. At some point they hit the wall, they neutralize, so they recombine, they become neutrals, atoms and molecules, and then they recycle back into the plasma. Now these neutral particles, we've seen they're not bound by the magnetic field, so they scatter all over and they will start interacting, colliding with your plasma. And this is actually a very wanted effect because by these collisions you can dissipate a lot of energy before the plasma actually reaches the surface, and so in this way you can protect your material surfaces by so-called high recycling or detached conditions. Now the problem is that if you want to simulate this, this becomes extremely expensive, especially if you have to trace individual particles. So what do? Well, we try to develop computational methods that on the one hand are very accurate, that are compatible with the kinetic description where you have high accuracy in the regions of the simulation where you need it. But in fact, if you have these local high dense areas with high collisions between plasma and neutrals, then your neutrals behave as a fluid. And so we try to somehow optimally combine those fluid and kinetic regions in the domain by devising what we then call hybrid models for the neutrals so that we can have very accurate simulations and at the same time very efficient simulations of the exhaust. And so with the Leuven group, we then implement all those models in the SOLPS ether code. So this is a very big edge code used internationally. It's used to simulate the exhaust scenarios for basically all existing tokamaks in operation today. And it is also the tool that is used for the design of the ether diverter and for most of the next generation demo reactors. So we're one of the leading development teams there. So we regularly implement our model improvements there. We also do basic algorithmic improvements and numerical studies on those codes and support the users in that. So you see a few of the logos here of the collaborators that we have here. So we work, among other, directly with the ether team and the demo design teams for the European demo machines. Okay, once we have then those accurate plasma models, we try to use them for design of the diverter. And so that's actually a very complex problem. So you have there a diverter cassette. And so at some point the design question comes, okay, how do I have to shape these diverter targets? And so in principle, every single point on the surface you could move. And you also at some point have to decide what your magnetic field in the diverter should look like, because by changing the shape in the magnetic field, you can redistribute where the power is going to hit the wall, and so you can improve the exhaust regimes. And so you have a large number of design variables. You have these expensive models that we have to solve. And at the same time, we have a lot of constraints with respect to how much space you have, where the machines have to be, whether erosion is tolerable, and so on. So this is a very challenging problem. And if you have to do this simulation-based for next-generation machines, one way would be to, okay, you set up your simulation, you have a certain number of inputs, there will be many of them. You do a simulation, which will be very expensive. It can take days or weeks for next-generation machines. And then you have a certain number of outputs that you will use to assess the validity of your design. Now what you have in practice is that the number of outputs is usually relatively small compared to the number of inputs. So if you're not satisfied with the output of your simulation and you want to redo a simulation, you cannot just go and change every single input and repeat the simulation because it would take you too much time, especially since the guy in the middle is there very slow. So what do we do in practice? Well, we try to be a bit more clever. Let's say we have some output of the simulation, which is an extremely localized peak heat load on the diverter. What we will then say is, okay, I want to make this heat load as flat as possible, below limits that can be tolerated by materials. I put the change between what I have and what I want into an adjoint simulation, and this adjoint simulation is going to give me as an output immediately how I have to change all my inputs at the cost of just a single additional simulation instead of tens or hundreds of new simulations. And so we have been working on these methods for quite a while now. And so we're actually able to treat now very complex design problems for the diverter, for the shape, for the magnetic field. And we develop also very efficient algorithms to solve this whole design loop in a cost that's not much more expensive than just a few simulations. So with this approach, we can now really start tackling the exhaust problem for ITER and demo. So here are just a few examples of what we have been able to achieve with this. So this is an example of diverter shape design, where on the left you have the test case inspired by the current ITER design, where you see that you have very peaked heat load, so the red curves here on the right towards the diverter target plates. And then by optimizing the design of the diverter, so by automatically changing the shape, we were able to get a fully horizontal, so flat heat load that's much more sustainable, hopefully, for a future reactor. And so you can also do the same by trying to optimize the magnetic field. So in this example, it's a bit difficult to see, but you see on the left an initial magnetic configuration where the X point is setting at a certain distance above the target's plate, and then by controlling the currents through your diverter coils, bringing the X point a bit closer, you can benefit of flux expansion to again reduce the fluxes towards your target plates. So these are all some examples of what can be done. In fact, exactly the same methodology can also be applied to try to estimate model parameters, so insert model parameters based on experimental data, and also trying to then get uncertainty estimates of your code predictions. And so those are also methods that we're working on. And then to conclude, I want to make one more step of the research. So we've seen already the plasma edge modeling itself. Then we have seen how that leads to scenario optimization and diverter design optimization. The next step that we want to take is to actually optimize the design of the individual components. And so there we're looking in particular at how you should build your monoblocks. So the monoblocks, those are the components that are really in the diverter directly in contact with the plasma. So you see each of the diverter cassettes has a number of plasma-facing units, which are basically tubes with a coolant flowing through them, and on these tubes you have the individual monoblocks. And so if you're not careful with your monoblocks, they can crack if they're loaded too heavily. And so why does this happen? Well, you have a lot of thermal stresses in these components, and especially if you have material interfaces, you can get local stress concentrations, which can lead to cracking. And so what do we do here? Well, we try to exploit the potential of new techniques, in particular functionally graded materials, where you can try to combine different materials like copper and tungsten that have each their own beneficial properties for the exhaust problem, and to combine that with the potential that is given by new manufacturing techniques like additive manufacturing. So if you have additive manufacturing techniques, you can start really on a very fine scale designing the detailed structure of your materials, and you can somehow optimize the composition of your monoblock, going from the very top surface where you want a very heat-resistant material like tungsten to protect your component from the plasma, and then gradually transitioning into copper towards a coolant, which has very good heat conduction properties. And so if you do this change in a gradual way, you can avoid local stress concentrations, and so therefore you can avoid problems like cracking and increase the lifetime of your component. Okay, and so with that, I already come to the end of the conclusion. So as you've seen with many of the other institutions, this is a very international research. So we have many collaborations ongoing with partners across Europe and across the world. And this is then just my summary slides showing that how we tackle the diverter exhaust problem by plasma edge modeling, then scenario optimization, and eventually coming to component optimization. So thanks for your attention, and if there are any questions,
Thank you very much, Dr. Dekeyser. Do we have questions?
Hi, very nice talk. As Jeff mentioned, we just had the DT campaign in JET, and one of the things that we really would like to find out, and where I have the impression you might be of big help, is because we have this tungsten diverter, we get high heat loads, we have sputtering of tungsten from there, and then that migrates towards the mid-plane, and because the plasma is rotating very rapidly, it tends to form a highly radiating blob, because tungsten radiates a lot because it has a high Z value. Would your codes be able to capture this kind of physics and get us an improved understanding?
Yeah, so very good question indeed. These codes would in principle allow you to, let's say, model where the plasma would strike the tungsten targets. Then if you have estimates of the erosion rates, we can then predict how this tungsten will travel possibly upwards towards the core and whether or not, and under which conditions it would form a radiating mantle or would penetrate, leading to unacceptable impurity contamination of the core. Yeah. So this is indeed what this kind of codes are used for. Yeah.
All right. Any other questions? If not, let's thank Dr. Dekeyser again.
Thank you.
Next presentation is a duo presentation by Professors Laurent, Delannay and Xavier Urbain from the UC Louvain.
Did you take the pointer?
I don't have the pointer, but that's okay.
On the desk?
On the desk? Is it that thing?
Yeah.
Oh, it doesn't look like it. That's why. Sorry. Okay, so the activity at UC Louvain is not in direct connection with the fusion machines, as far as I know, at least not mine. So we have two institutes that are involved in this kind of research. So I'm personally at the Institute for Condensed Matter and Nanosciences, this IMCN, and Thomas Pardoun and Laurent Delannay are the Institute of Mechanics, Materials and Civil Engineering, if I'm not mistaken. And we contribute in different ways to the ongoing fusion research. So we have, as an atomic and molecular physics group at UC Louvain, been involved in the constitution, the filling of a huge database of atomic and molecular data like cross-sections, branching ratios, emission spectra, for the different needs of the fusion research. And you probably all know that, and we just heard that the problem comes back. So the first fusion machines couldn't sustain the plasma just because immediate erosion of the walls would produce multiply charged ions that would, in the end, recombine and radiate and would quench the plasma. So we had some continuous activity for about 20 years on this characterization of single and multiple ionization of multiply charged ions of different kinds. So there were studies on easy elements like carbon, nitrogen, argon, krypton, but some on metallic species as well, like nickel, for instance. And you probably all know that the charge state of these metal impurities is a measure for the temperature of the plasma. And so this is for iron, the sequence of multiply charged of charges that would dominate the population of iron in the plasma. And so for the sun, which has a corona in the millions of degrees, that's where you would find emissions peaking around just below, I think, iron ionized 16 times. So ITER would be even further, and the whole sequence is actually developing from the wall to the core of the plasma. So how would you do that? That's just an old picture just to tell you, of course you have to make those ions, you have to prepare them in an electron cyclotron resonance source, accelerate them, form a beam, try to cross it with an electron beam if you are interested in electron-ion collisions, and you have to get some quantitative measurement, and we developed different techniques like animating the electron beam just to avoid the uncertainty in the overlap of the beams. So, okay, this problem of wall erosion was sort of circumvented with the plasma limiters, and the first ones were carbon, so graphite, if you like. And this carbon, as was mentioned, that was a nasty component to introduce in the plasma because that would form hydrocarbons, and these hydrocarbons would end up with kind of tar that would contain tritium in the end. So that was very bad. So this machine that was studying multiply charged ions could be used to study the destruction and evolution of carbon-containing molecules. And that would be, for instance, methane with deuterated methane that would get ionized and dissociated. And the same type of chemistry, because we could call that plasma chemistry, would come when you introduce nitrogen on purpose to cool the plasma in front of the diverter. That's what is on the bottom here. It doesn't work, that doesn't matter. So you could introduce nitrogen on purpose and hope, and this has been demonstrated to work, that destruction of this molecular nitrogen and in the end, ionization, multiple ionization of the nitrogen atom would produce the radiation that you need. So this is one kind of studies we perform. And the other studies concern the heavy particles. So how would an ion interact with a neutral molecule that desorbs from the walls? And for that, we have developed techniques that allow us to cover a very large domain of collision energies, which is called the merged beam technique. So you have beams traveling together, and they could travel at the same speed and then interact at very low energy. And the very low energy I'm talking about is we can go down to something like a temperature of 30 Kelvin in the beam, but we can as well go to millions of degrees, provided the beam energies or beam velocities are different enough. So this is the kind of measurements you can perform. This is an example, just proton on H minus. So you would wonder why we are mentioning negative ions. And of course, there is a very timely application of those in the production of the future neutral beam heating systems. So there is, and it's already under testing, this demonstration of a very intense, very energetic D- ion source, which will be used to heat the plasma in ITER. And for that, there are many unknowns. So the source is already built, and still people don't know exactly how negative ions are produced and how they survive the plasma in which they are produced. So they have circumvented the problem by introducing segregated plasma. So you have a hot plasma to ionize and a cold plasma to recombine. But still, there are unknowns, and so we are collaborating with people at University in Germany and IPP as well, to try to constrain the reactions of the D- that we want to extract from the source with the cations, the positive ions that are present in them. So that's the kind of studies we can of course perform as well. And for neutralizing the D-, there are proposals to use photo detachment, so use extremely powerful lasers. And for that, we have done recent measurements that constrain the probability of such processes. So I think it's time that I leave the floor to Laurent Delannay, and I'll let you
Thank you, Xavier. Welcome. Good morning to all of you. So I will use a few words to describe the second line of research at UC Louvain, quite different, independent of the first one, justifying that we have two different presenters. So now we are focusing on those structural components of ITER, what Dmitry Terentyev had called the box around the sun. And you remember from the previous talks that these components, they are hosting huge temperature gradients, meaning also that the thermal expansion will be quite different on one side compared to the other side, and this will lead to huge stresses, potentially leading to damage. One of the big issues, as you also heard from the previous talks, is that nothing is really stable, constant in the plasma. There are instabilities, there are fluctuations in temperatures, leading thus to fluctuations in the loads, in the mechanical loads, and you may know that materials don't like fluctuating loads because they are likely to promote cracks. So how can we contribute to the assessment, to the validation of these components where tests are being made? You heard it in MOL, in SCK. A lot of them, they are characterizing, and one of the important things also to mention, if you don't have a background in material science, is the fact that this temperature not only creates the loads, but also has an effect on the material response. The response of tungsten is not the same at high or low temperature. It's also depending on the rate at which you are loading the materials. And all of this has been characterized, but as you can tell from this figure, this has been done and must be done at the macroscopic scale, whereas the issues, the problems, the damage, they are arising at the microscopic scale, the micron scale, at the scale of the polycrystal. And this is where we come into play. We have an expertise in Louvain about the modeling of so-called crystal plasticity, really modeling plasticity at the scale of individual grains, where we know that dislocation glide occurs along different planes in the different grains. They are very anisotropic. The behavior of the grains is very anisotropic, leading to stress concentrators, which are at the origin of damage of the cracks. So we have looked at that using the data from SCK and using that into models to predict what is occurring at the surface of the plasma-facing components. This is modeling. We are not only doing modeling, also doing experiments and looking at other components also made of, this is Eurofair, where the behavior in this case is ductile, which are the failure, if expected, would be ductile. And there too, there is a very good expertise in Louvain. And this involves, as you see, some modeling, but also experiments. We were doing a lot of those too, to characterize the materials, also involving, you see, tomography on the bottom left there, to really see how the damage is occurring inside this metal. There are several ongoing researches, in most cases, if not all cases, I think, involving SCK in close collaborations. Another thing of interest and quite original, I think, is to try to miniaturize the test. You know that we don't like, especially when we have to irradiate the material, to see how the neutron irradiation is influencing the material behavior, how it's embrittling the materials. We don't like to have too big volumes which are activated, so we like to make small test specimens, and these ones are extremely small. They are made by electrodepositions. We are using techniques used in microelectronics to produce microelectronical components, but this time we have adapted these techniques to produce micron-scale tensile test specimens and try to extract the material behavior there, based actually on the stresses, the deposition stresses, residual stresses, which are used then to pull on these different samples. This has been controlled, optimized now for tungsten. We were doing this on other materials than tungsten, now adapted this to tungsten. And the ongoing research, as you can see on the slide, involves looking at the propagation of cracks, the toughness of tungsten using these films. And then the next step will be to go into irradiation and creep irradiation on these thin films. Now, important question you see on the bottom is whether these experiments here would be any relevant when compared to bulk macroscopic samples. What we will do is rely on models to compare what is being done, what can be done on the thin films and also on the bulk samples is nano-indentation. And using these experiments and also crystal plasticity modeling, we hope to confirm and extract information from the thin films that is useful also for the assessment of macroscopic components. And this is the end of my talk. Thank you to all of you.
Thank you very much, Professors Delannay and Urbain. Are there any questions? No immediate questions. There's going to be a lot of time to discuss later. Then let's thank our speakers again. And then we move to the final talk of the session. We started in Brussels, we come back to Brussels. Ms. Yelyzaveta Velizhanina from ULB is going to present the research on behalf of the lab in Brussels, ULB.
Hello? Yeah, okay, it works. Thank you for this introduction. I will be presenting the research activities of our Fluid and Plasma Dynamics Research Unit on behalf of my supervisor, Professor Bernard Knappen. He apologizes for not being able to attend. So first, let me briefly outline our main research focus. We majorly specialize in modeling liquid metal flows under the influence of magnetic fields. Our research field is known as magnetohydrodynamics, or I will refer to it as MHD. Basically, MHD is coupling between the fluid dynamics and electromagnetism. Over the recent years, we have mainly focused on studying certain MHD flows, such as flows over flat plates or boundary layer flows. I will use boundary layer flows, then flows on concave surfaces, and also flows through ducts and pipes. And all these flows are subject to applied magnetic fields. Besides, we are engaged into software development. In particular, we developed and now we support certain modules of computational fluid dynamics solver, YELS2, that is maintained in Rouen in France. The major scope of our research is stability of liquid metal flows in the presence of magnetic fields. To briefly introduce the concept of stability analysis, please consider this figure. Here we simply display that in the airflow past a sphere, there are regions where the flow is regular or laminar, and then there are regions where the flow is very complex and disordered or turbulent. The stability theory aims to define the conditions under which the transition between these two states occur. The main framework of stability analysis consists in linearizing equations of motion. In our case, it's the Navier-Stokes equations, and then determining whether small perturbations injected into the linearized equations grow to the point where nonlinear effects become important, making it possible for transition from laminar state to turbulent state. I will be discussing two particular examples of MHD flows that we studied, that we focused on in our research. First is the flow over the flat plate in the presence of span-wise magnetic field, so magnetic field that is perpendicular to the direction of the flow but parallel to the wall. Such flows occur in plasma-facing components of fusion reactors. In the current figure, we display the cross-section of a tokamak, such as ITER. In certain designs, the plasma-facing components in tokamaks are coated with a thin layer of liquid metal to reduce structural damage to a solid wall. In the boundary layer, in the absence of magnetic field, there occur unstable structures. Here we display how it looks. They occur in the form of longitudinal streaks, and as they evolve, they break down into the patches of turbulence that you can also see in figure. Our research focuses on such questions as how does the presence of the magnetic field, of the span-wise magnetic field, affect this instability, whether it modifies it or even suppresses it. And here I will present a little bit of results of this research. In figure on the left, we show the temporal evolution of kinetic energy of small perturbations in MHD boundary layer. The applied magnetic field is of relatively low intensity in this case, and the growth of perturbations is reflected by the growth of their kinetic energy. When the amplitude of perturbations reaches a certain level, then there occurs transition to turbulence, which is reflected by fluctuations of kinetic energy. Different curves in this plot correspond to different initial levels of kinetic energy of perturbations, and you can also see that, in fact, certain minimum initial kinetic energy is needed to be able to trigger that transition to turbulence. In the movie on the right that I'm going to play in just a few seconds, we display the temporal evolution of isosurfaces of kinetic energy of perturbation in MHD boundary layer flow. So I will play it. At first, these perturbations were aligned with the magnetic field. Then they gained energy through the mechanism known as vortex tilting. Eventually, there occurs secondary instability, and you can observe the breakdown to turbulence. More results concerning this research were presented in the article reference in the current slide if you are interested. And I will proceed to the next example of the MHD flow that we considered. This is the MHD flow through a circular pipe under the influence of transverse magnetic field, as displayed in this sketch. To motivate this research, I will return to a liquid metal plasma-facing components in fusion reactor. In this schematic image, we show one of the designs of liquid metal blanket, which is essentially an assembly of pipes and ducts where the liquid metal is circulated under the influence of a strong magnetic field. And this flow is notable because the transverse magnetic field modifies the base velocity profile. As you can see in these ISA contours, in the absence of magnetic field, and then when you have applied the transverse magnetic field, first of all, it breaks the symmetry in the base velocity profile, and then it also leads to the occurrence of thin boundary layers, inflection points, and we try to address a question whether this makes these MHD flows susceptible to magnetic instabilities. And it turns out that in the presence of transverse magnetic field, in certain flow regimes, there arise unstable structures in the form of a pair of high and low speed longitudinal streaks. In these two plots, we show the Iser surfaces of velocity fields of these streaks for lower magnetic field, for lower intensities of magnetic fields, and for higher intensities of magnetic field. And for lower intensities of magnetic field, they are localized near the center of the pipe, and then when you increase the intensity of magnetic field, they move towards the wall of the pipe. Since it happens to be the topic of my PhD thesis, I am also presenting a poster today, dedicated poster, and we will be also presenting an oral talk on the international conference in Krakow this summer. Now, a few words about our other activities. As I said in the beginning, we are engaged in software development. First, we develop our own linear solver that is concerned with stability of MHD flows. And second, we develop a certain module such as MHD module and porous media modules of computational fluid dynamics solver YELS2 maintained in Rouen. A few words about YELS2. YELS2 is a massively parallel solver that can run on tens of thousands of processors. It can deal with very complex geometry because it is based on finite volume discretization method on unstructured grids. Besides, it has the functionality to model unresolved scales in turbulent flows by adding large eddy simulations subgrid models. And a few words about our MHD module that we developed. It uses a conservative formulation, which is very important to be able to deal with a very wide range of intensities of magnetic field. And finally, more recently, we focused on coupling YELS2 that I just talked about with ParaView catalyst library. ParaView is the library that provides a lot of tools for visualizing your three-dimensional data and also post-processing, which you probably know. Having integrated YELS and ParaView Catalyst, we will be able to visualize the solution of equations of motion live as it's been computed. And besides, we will be able to significantly reduce memory requirements for post-processing. At this stage, we have only managed to implement in situ visualization of unstructured grids. These are just few examples. Our next step will, of course, be to implement in situ visualization of scalar and vector field that are being computed by YELS2. And this is it, what I wanted to tell you about today. Thank you for giving me the stage, and if there are any questions.
Thank you very much, Ms. Velizhanina. Are there any questions?
Is there any activity at ULB in the framework of the broader approach for IFMIF?
For what?
IFMIF, the fusion material irradiation facility.
Well, I know very little about it, but I know that there are experimental labs that study the interaction of materials with plasma, but I don't exactly know their framework and motivation. But I have been told that they could, in principle, engage in Eurofusion program if they wanted, so I assume yes. But I don't know the details.
Guido, the work there was started with IFMIF. The work with ULB and Bernard Knappen on lithium flow and magnetohydrodynamic was started on IFMIF in the year 2008, 9, 10, maybe. I don't know if they are still busy with that, but afterwards it has been deviated towards the use of lithium flow inside the tokamak.
All right, thank you very much. Let's thank the speaker again.